So welcome back. In this video we're going to discuss second order Fréchet derivatives. Of course we're all used to second derivatives in calculus, right? So we have the derivative, which is a limit. If we take the derivative of the derivative, we get the second derivative. Well, I mean, this is speed, this is acceleration. And of course, first and second derivatives pop up everywhere. And we have the higher dimensional versions where we take partial derivatives of all kinds. I'll ask you that you bracket all of this or forget all of this for the time being, because we're going to be talking about a much more abstract concept of a Fréchet derivative. I mean, the Fréchet derivative itself is already kind of abstract. Now we're going to talk about something even more abstract, which is derivative of a derivative, and we're going to try to make sense of that. So this video is mostly about definitions and ways of conceiving what's going on, understanding what's going on. I mean, it requires a certain level of abstraction, which you'll have to get used to, as in with many other things in the subject, but I don't think it would be a big problem. We just need to understand what's going on. So let me actually correct, even the first slide I have a little bit of a problem. But okay, these symbols probably don't make any sense to you right now, so okay, let's get started, and by the end of this video everything will be clear. We have our usual setup, right? So we have our Banach spaces V and W, we have an open set contained in V, and we have a function which is defined with domain U and counter domain V. And now we know what the Fréchet derivative is. Well, it's a linear operator, a bounded linear operator from V to W, such that if I take a sequence, well, I take vectors age going to 0, right? X naught is a point in U, so for all small enough age, this belongs to U if norm of age is small. And it points that you can write f of x naught plus age is equal to f of x naught plus a derivative operator applied to age plus a term that when you divide by age, norm of age, sorry, right, this goes to 0 when age goes to 0. That's a definition of the Fréchet derivative. Now, assume that derivative is defined not only for x naught, but for all points in U. Not only for specific x naught, but all points in U. Therefore, you have a new function, which is a derivative function, right? So what does this function do? It takes a point x in the domain of f and produces a linear operator from V to W, which is a derivative at x. So the derivative map is a map from the open set U to the space of linear operators from V to W. I mean, that can be a little bit confusing, right? So the derivative at any point is a linear operator. Therefore, the derivative thought of as a function, associate a function from U to the set of linear operators, associates with each point the derivative. And the derivative is a linear transformation, so that you can apply the derivative of x to any vector age. Is that confusing? Hopefully not too much, right? But it's just saying, okay, this thing here is a mapping that takes a point x and gives me a linear mapping between V and W. Okay, here's something that we know from a previous exercise. This guy here is a Banach space with that norm, V arrow W. Right, the norm the norm of T is just a soup over non-zero vectors V of norm of TV, that's an element of W, divided by norm of V. So we know this guy is a Banach space. Therefore, we have a function, which is this function here, df, that maps an open set in a Banach space to another Banach space. We can talk about the derivative of this function. And of course, the derivative of the derivative is the second derivative. So all I'm saying is that I'm allowed to speak of second derivative simply because the derivative itself, in this case here, where f is differentiable over the whole of u, so you have the derivative as a map from u contained in Banach space to another Banach space. Okay, what does that look like, right? So, okay, again, right? So if df is well defined, therefore it's a mapping between an open set in a Banach space to another Banach space, we can talk about its derivative. And what is a derivative, right? So, okay, u is contained in v. And we know that if you're talking about the derivative of a function, it's a linear mapping from the Banach space on the left-hand side, which is still v, right? So u is contained in v. Well, it's a linear mapping from v to the Banach space on the right-hand side, which is this guy. So it's a linear mapping from v, as a bounded linear transformation from v to the space of bounded linear transformations from v to w. So that's a bit confusing, but let's, okay, if you want, call this Banach space here x, and then you have a mapping from an open set in v to x, and here you have a linear transformation from v to x. So that perhaps doesn't look so threatening, right? And of course, the definition of the derivative of the derivative is just that if I compute this function here, right, df at h naught plus h, and I subtract df at x naught, and the derivative applied to h, when I divide everything by the norm of h and set h to 0, this thing should go to 0. Or, in this other way, I sometimes write things down, the derivative at x naught plus h is equal to derivative plus the derivative of the derivative applied to h plus little o of h, which is just something that when divided by h goes to 0. Now, the important thing here is that, okay, we're doing everything, so the counter domain to the space x, the space of linear transformations from v to w. So we need to use the corresponding norm, and the norm is this norm v arrow w. But outside of that, there's nothing weird going on, right? So there's just, I have a space x, I'm using the norm of x, and everything's as it should be. But of course, this is perhaps not the most exciting definition. I mean, let me put it another way. I mean, not only is it not too exciting, but it looks unwieldy. It looks hard to work with. It looks kind of, doesn't have much to do with the original f. And the point of the remainder of this video is to try to make sense of this and find a perhaps more concrete way of thinking about the derivative of the derivative. And in order to do that, we need to understand this funny space, right? So remember from the previous slide, the derivative of the derivative belongs to this guy, right? So, sorry. The derivative of the derivative of x, of f at x naught belongs to this space. When it's well defined, it belongs to this space. So, okay. This is the space of linear transformations from v, bounded linear transformations from v to the set of bounded linear transformations from v to w. So what does a t here do? It takes an element of v, this v1, and maps it to tv1. And what is tv1? tv1 is a linear mapping taking elements of v to elements of w. So it takes a v2 in v and maps it to linear transformation tv1 applied to v2. Now we have the following facts. We know that the mapping from v1 to tv1 is linear. Therefore, if you compute something like lambda v1 prime, apply t to this should be lambda times t v1 plus t v1 prime. And I mean, here we're using the operations defined in the set of linear transformations, right, in this guy, which we know is a vector space. So everything's well defined. We also know that when you fix v1, this tv1 is a linear transformation from v to w. So we have a similar thing. So maybe I should write that in a single slide. And, sorry, I need to add a page. I want to write that by itself. because this is a key to everything that follows, right? So I want to compute T lambda V1 plus V1 prime applied to a certain V2. And that, as we argued, is lambda T V1, right? So I'm using here the fact that T is linear. V2. And of course, we know that the operation, right, these are elements in LVW. And we know these operations are defined so that I can write now that's one thing. And another thing is that if I take TV1 and apply this to lambda V2 plus V2 prime, well, TV1 is a linear map, so that's just lambda TV1 applied to V2 plus TV1 applied to V2 prime. What I'm hinting at here is that this, that this map here is bilinear, meaning it's linear in V1, and it's right. So I'm taking V1, V2, and mapping it to TV1, V2. And what I'm saying now is that this is a bilinear mapping. And I think that should be clear from the slide why that is. And yeah, so that's what we're going to do next. So we're going to argue that this funny space of bounded linear transformations from V to bounded linear transformations from V to W is actually essentially the same thing as this more familiar set of bilinear transformations from, well, we used to write it as like VVW. It's a set of bilinear transformations from V times V to W. But I'm just going to write it like L2VW. Right, so I'm going to argue the following, that you can find a very natural bijection between elements of this space, so linear transformations from V to linear transformation from V to W, all bounded. We can find a natural bijection between that and the set of bounded bilinear maps from V to W, from V squared to W, if you like. And this bijection preserves the natural norms in this space. The main difficulty with this result is that we have to write down the proof of something that's, well, either mysterious or very obvious. I find that with all students, you know, there's a time t0 before which everything looks mysterious. And maybe there's a kind of tiny interval around t0 where maybe they're trying to figure out what's going on, but it's starting to make sense, and then there's this aha moment, and then it's obvious. And proofs like this are kind of hard to write because, well, I mean, basically I'm just going to tell you what the proof is. There will be some checking involved, so I'm going to leave some things for you to check. And once you do that, maybe you're still going to be confused for some time, but then you're going to stare at the theorem for long enough, and suddenly the truth will become self-evident. But okay, so hopefully that's not going to take too long. So let me show you what the proof is. Right. First of all, let me remind you of what are bounded bilinear mappings. Okay, first you have this map from V times V to W. Well, it's bilinear if it's linear in each variable, right? So it's something like, well, if I look at V1, V1 prime, V2, then you get a linear combination. And the similar thing if you change the second variable, right? If the second variable is a linear combination. That's bilinear. What does it mean to be bounded? Well, it means that this norm here is finite. This is a fact that we didn't show. Well, it's an exercise. Remember, we showed that the space of linear mappings from V to W is a Banach space with a natural norm. it turns out that the space of bilinear mappings from V squared to W is a Banach space with a natural norm as well. And the proof is exactly the same. So I'm not going to repeat it. I'm just going to leave it as an exercise. And I mean, it's a nice exercise to do, but what you should do really is to grab a piece of paper, have the proof that the space of linear transformations is a Banach space on the side, and try to copy it and make sense of it in this setting of bilinear things. And that's all there is to it. Okay. Now what do we do? Let's try. I told you that'd be a bijection, taking linear mappings, bounded linear mappings from V to LVW to bounded bilinear mappings. So what is a bijection? Remember, T takes a vector V1 and produces a linear transformation from V to W. The linear transformation takes a vector V2 and produces an element. Sorry, this is wrong. Produces an element of W. Okay. So what is Q of T, right? So Q, remember, Q is going to be my mapping. So given T, I want to produce a bilinear transformation, which is Q of T. Well, that's really simple. It's what I wrote a few slides ago. I just take the transformation that takes V2, write an element of V2, there it is a pair of vectors, and produces TV1 applied to V2. Now there are several things we need to check. One of them I've already checked, which is that Q of T is bilinear, meaning that if I take linear combinations in the V1 position or V2 position, I get linearity, right? So in each one of these variables. That's been done in that slide where I just spelled everything out. Now there's another thing you need to do, which is to check that Q is a linear map, meaning if you take lambda T1 plus T2, then you get lambda Q of T1 plus Q of T2. Okay. Then we also need to check that this bilinear map we need, right? So we need to show that this guy actually belongs to the space of bounded bilinear mappings. We haven't done that yet, but we'll do it. However, instead of doing that first, let me show, okay, believe in me for a second that this guy here is a bounded bilinear mapping. So I have this map Q from L of V to LVW. That's to L bilinear from V to W. What would be the inverse map? And I'm going to define that now. The inverse map is really simple to define, right? So what does an element, okay, take a bilinear transformation from V to W, bounded. It takes a pair of vectors and give me a pair of vectors. And give me Q of the pair of vectors. So what's the associated element in the space of linear mappings from, right? So I want this guy to be in L of V to L V W. So what do? I take this map, tau of Q. It's going to take as input a vector V right here. V1 is here. And I'm going to produce as output an element of this space. And this output is just, well, take the, right, what this is doing is take the bilinear map, Q, fix V1 as the first element, and let V2 vary. So if you like, well, I have this, I want to define TQ V1, and I want to show how it acts on a vector V2. That's just by definition Q of V1, V2. That's a definition. Right? So I'm just saying, if you fix one of the entries in the bilinear map, what you're left with is the linear map in the other entry. And now what you have to check is that this thing here is a linear, right? Tau defines a linear transformation from L2VW to LVW. Now, okay, the first thing is to show that if I give you a bilinear transformation, this new thing gives me a linear transformation from V to the set of linear transformations from V to W. And then you need to check that everything's bounded, but let's forget about that for a second. Well, you have to check that in the end. Right? So as I said, there will be lots of things for you to check. But what we are going to do now is to argue that the original map Q preserves norm. And what does that mean? I want to show that the norm of T as a linear transformation from V to LVW is equal to the norm of Q of T, which is a bilinear transformation from V to W. And here's how we do it, right? So what's this transformation norm that we define, right? So if I have here X, as I talked before, the norm of a linear transformation from Banach space V to Banach space X is just a supremum of this ratio, norm of TV1, and divided by norm of V1. Here I have the norm of space X, which is a space of linear transformation. So I have this arrow. And okay, how do I compute this norm? Well, okay, keep the soup outside. This norm here is this guy inside the parentheses here. Sorry, this is again wrong. I need to write this properly. This is just TV1 applied to V2. Remember, TV1 is a linear transformation. How do I compute the norm of TV1? I apply it to vectors V2, look at the ratio of the norm TV1 applied to V2 divided by norm V2, and take the soup over all non-zero V2. Okay. Now there's a non-trivial step in the proof, which is this equality here. Basically what I'm saying is that you can move the soup here, the soup inside, you can move it outside. You can take the soup together in V1 and V2. And why is that? So basically I'm using a very general statement here, which is that if I take a soup, right, I have a function from A times B to R, and I'm gonna even look at extended R, I can take the values plus and minus infinity. So what I'm saying is that I can take the soup in the two variables in any particular order, it doesn't matter. So if you like, well, this proof in my lecture notes in Portuguese is not a hard exercise to do, but if you accept that, then you understand the step. Because now what I did before is I took the soup and I moved it outside. So I'm taking a soup in V1 and V2 together, both non-zero, of TV1 applied to V2 divided by the product of the norms. Now this guy here on top is Q of T applied to V1, V2. And so if I look at the supremum here, right, the supremum here, that's just the norm of this bilinear map. Remember, the Q of T is a bilinear transformation. So taking the soup of TV1 applied to V2 divided by the product of the norms of V1 and V2, that's just taking the soup of Q of T applied to V1, V2 divided by the product of the norms, and that's the norm of the bilinear transformation Q of T. What does that prove us? Well, I mean, in reality, this should come after part 1 of the proof. It's just saying that, okay, given a linear transformation from V to LVW, a bounded linear transformation, I showed you how to produce a bilinear transformation from V squared to W. Now, what I've argued is that this transformation from T to Q of T preserves norm, and therefore, if I start with something that's bounded, right, that belongs to LVW, I end up with a bounded bilinear transformation. And in fact, what you can show is that also this inverse map has the same property, that T of a V, right, so as a map from V to LVW is equal to the norm of Q as a bilinear transformation from V squared to W. And that's how you wrap up the proof. So what you have to argue is that, okay, map from T to Q of T is a linear bijection that preserves norm. It's a linear map that preserves norm between these two spaces, right? So that the map tau is the inverse of this, and it also preserves norm. And now we have a function from LV to LVW, and an inverse function from L squared V to W. Right. So you have sorry, let me say it again. We have a transformation from LV LVW to L to VW. We have an inverse for that transformation, therefore the original transformation is a bijection. and it's a linear bijection with linear inverse that preserves norm. Right. So again, there are lots of things to be checked, but trust me, everything works. And okay, from now on, we should try to get comfortable with this thing. What are we saying? I'm saying the following, that the derivative of the derivative is a linear map from V to linear, bounded linear map from V to bounded linear map from V to W. But we're going to think of the second derivative as something slightly different, which is a bilinear transformation from V to W. And the point is that these two things are connected by this isometry that I just defined. It's an isomorphism of normed vector spaces. In the sense that it preserves the structure of vector spaces. It's a bijection, it preserves the structure of vector spaces, but it also preserves the norm. And how do we write this down? Okay, so we know something like this expression if this is replaced by d of df x naught. We showed that before. That's just the definition of the Fréchet derivative of df. But now we just saw, right, so that we can relate elements of LV, LVW to bilinear transformations like this, to bounded bilinear transformations like this. So that's all I'm going to write. So df x over w, look, this is a linear transformation from LVW. This is also a linear transformation from V to W. This is a bilinear map. So when I fix one coordinate, that's now a linear transformation as well. And then I just want to say this is equal to this guy is equal to this guy plus this one plus this small term. And another way of putting it is, if you like, okay, this is as I said, this is a linear transformation, a bounded linear transformation. So if I want to know what it's like, I'd better apply it to elements of V. So when I do this, I have an element of W. And just from the previous slide, you know, okay, there's another element of W. Now, I took a bilinear thing from V to W and computed it on a pair of vectors. So this guy here also belongs to W. And then I get a remainder term. And of course, the remainder term should go to 0 when divided by h, when h goes to 0. However, you get a stronger property. And that's just from the definition of the norm, right? So you just look at the norm of the difference, right? So what we have here, we have, okay, I claim that this is what you're going to get. And let me argue in the next thing how you get that. So we have the following. df x naught plus h minus df x naught. So let me write it in the language of derivatives. X naught applied to h. This is right. So this is these are elements of LVW. So you have to use the norm. Sorry, these are elements of LVW. You have to use the right norm. So when you divide by that, everything should go to 0. And that's if and only if 1 over h v. So now I'm going to compute right, the norm of this, right, again. This is a linear transformation. So if I want to compute its norm, I take the sup over v, non-zero, df x naught plus h v minus df x naught v. Need more space. df x naught plus h minus df x naught maybe put it like this. df x naught h v. That's, so I'm just computing, right? So I'm just computing. So okay, let me forget about the limit when everything goes to 0. I just want to argue these two expressions are exactly the same, because if I want to compute a norm like this, what I have to do is to take a supremum like this. Now what happens here? If I, let me say, sup in V not 0, what happens here? Okay, I'm taking this linear combination of linear transformations and I apply V to it. I apply this combination to v. So I get df x naught plus h v minus df, so no brackets, x naught. So what am I doing here? Now comes a crucial step. Remember, this guy here belongs to the space of linear transformations from v to linear transformations from v to w. So when I apply h to it, I get an element here of linear transformations from v to w. And then I apply this linear transformation to v. But we know, and that's the point, we know that this thing here, by definition, is exactly the same thing as taking a bilinear map, which is a second derivative, and applying it directly to hv computer, and now we compute the norm. So that's where you use the isomorphism. So these two guys are isomorphic, this guy and this guy. Therefore, right, so by assumption, if d is differentiable, df is differentiable at x naught, the top thing goes to 0 when h goes to 0. Therefore, that's the same as requiring that this thing with the supremum goes to 0 when h goes to 0. So that's just another way of writing things down. I mean, you have to believe your isomorphisms, and then everything works. It looks magical, or maybe it looks completely confusing and useless. It's neither one of these things. It's perfectly sensical. It's just something you need to check carefully. Hopefully once in your lifetime. And then you get used to it. Okay, one final thing in this video. Let's look at one specific concrete example. Okay, and I want to look at the case when V is the Euclidean space and W equals R. Remember that in that case we recover the gradient as an expression for the Fréchet derivative. I mean, we showed, okay, if f is Fréchet differentiable at x naught, the gradient is well defined, and then we proved this, the gradient is well defined and continuous, then f is Fréchet differentiable at x naught, and the derivative is just the inner product with the gradient. Okay, but in any case, let's assume that we know f is 2 times Fréchet differentiable and see what we get, right? So, okay, so then we have our expression. We have that derivative applied x naught plus h applied to v. That's just a gradient of f of x naught plus h applied to inner product with v. Derivative at x naught times v is this. Then we have this guy, which we don't understand yet, and we have the remainder term. So we want to understand what's going on here. We want to understand this bilinear transformation, and basically we only need to understand it over the canonical basis vectors. I mean, it's like a linear transformation. You know exactly what it does if you know what it does to the canonical basis vectors, because all other vectors are linear combinations of the basis vectors. So we're going to apply the same trick with a bilinear thing, and we'll see that it makes sense. Okay? So I'm going to take h to be this guy, which is going to go to 0, so t is going to go to 0, and v to be this guy. So when I look at this expression here, and I see what happens, I get, well, gradient of f of x naught ti times eh. We know that the coordinates of the gradient are just a partial derivative. So this is what I get here without the EF. So now if I look at the difference between 1 and 2, this is 1, this is 2. Right, okay, they're all applied with V. So I divide by t, right? So t here, notice that t is the norm of h in this specific example. So in any case, absolute value of t is the norm of h. So I'm dividing by t, and I get, when I look at the difference between these two guys divided by t, I get a quotient for the jth partial derivative when I'm varying the ith variable. And what do you get from this? So, I mean, I claim that when you do this operation, right, so what you get in this term here, you get d2f of x naught applied to ei times the h, and you get a factor of t in front. So when I divide everything by t, this t cancels, and I claim that you can prove, just from the, remember that the remainder term goes to 0, when divided by the norm of h. So it goes to 0 when divided by t. And just by applying this, you can check that this second Fréchet derivative applied to EI, is going to be the limit of this quotient for the jth derivative when you vary the ith variable. And what is that? That's a partial derivative, the ith partial derivative of the jth partial derivative. So it's a second order partial derivative from what we know from calculus. If you take out, this is for canonical basis vectors. So we know that somehow the bilinear transformation for the Fréchet derivative is related to the second partial derivatives. What happens for general vectors h and v? So if I want to compute this, I can just use bilinearity and decompose, right? So h is the sum of h I, ith coordinate, ei, something similar for v. And we'll end up with this expression. We just do, sorry, this should be d. We just do this decomposition, apply bilinearity, and we end up with this. And this, of course, has a form of a vector in a product with matrix times vector. And what is this matrix? It's a Hessian matrix. The matrix with entries given by the partial derivative of f at x naught. So just like we found the gradient as giving us the expression for the first Fréchet derivative, we now find that the Hessian matrix that we all know from calculus gives us the expression for the second Fréchet derivative. But does it follow that the existence of the Hessian that implies that f is twice Fréchet differentiable? Well, the answer to that is an emphatic no. We know that the existence of partial derivatives doesn't imply that f has one Fréchet derivative, and the same holds here. I'm not going to prove it, I'm not going to give a counterexample, but that's also true. However, when f is Fréchet differentiable, we know that the bilinear form d2f of x naught is given by the simple expression. Is applying the Hessian, is looking at the quadratic form defined by the Hessian. Right, the quadratic form is always something like, when you look at something like this for a matrix A. And this is it. One last thing. Okay, I told you. Does the existence of partial derivatives imply that f is differentiable? No. Does the existence of second partial derivatives imply that f is twice differentiable? That's also not true. However, we do have a partial converse. So we know that when the gradient is continuous, then f is differentiable at all points. The same result, you just apply it to the gradient now, means the following. Okay, I'm actually going to do it in a multivariate setting. You have a function between Rd and Rk. Assume that all partial derivatives are well defined at all points of view, and moreover that they are continuous at x naught. Then you can show that f is twice differentiable at x naught. The proof again is an exercise. It's not a hard exercise, but we're just using a criterion, right? So we want to differentiate the derivative, which is a map from U to L, linear transformations from V, which is Rd, to Rk. So okay, let me do it for k equals 1 because it's a little bit easier. So just looking at gradient as a function from U to this space. Well, linear transformation from Rd to R, just by this representation theorem, they're given by vectors. So this is essentially Rd. And what you have to argue is that so basically that, okay, you have the gradient. So you have to argue that df is differentiable if and only if the gradient is differentiable. And then we can apply the criterion that tells us the existence and continuity of partial derivatives is enough to imply Fréchet differentiability. Right? So of course the partial derivatives of the gradient are the second partial derivatives of f. So if the second partial derivatives of f are continuous, the gradient is differentiable, and that's the same thing as saying that df is differentiable. Okay? So that's a good thing because now we know how to take second derivatives of a lot of functions from Rd to R, or from Rd to Rk as I put before. Because all we have to check is that these functions, well, they're coordinates, they have continuous second derivatives at all points, and that's enough to ensure differentiability. Of course, I mean, that's not always true. There are functions that are differentiable we don't have continuous second derivatives, but the point is more like the other way around. So it's sufficient to have continuous second derivatives for the function to be twice Fréchet differentiable. And you can probably spot a pattern. We're going to show eventually that a function is 87 times, right, if it has partial derivatives of order 87 at all points, and these partial derivatives are continuous, then the function is going to be 87 times differentiable. But that comes later when we talk about partial derivatives of higher orders. For now, this is it. Thank you.